Okay, let's unpack this. Think about how much artificial intelligence has, well, fundamentally reshaped our world, how we live, how we work, how we interact with information. I mean, from the chatbots that engage in surprisingly human-like conversation to the sophisticated systems that can, detect complex diseases in medical images, AI's impact is undeniably profound. It's everywhere. But as remarkable as these achievements are, there's a growing sense, isn't there, that current AI models, the ones built on classical computing, might be approaching a kind of invisible ceiling. Consider the sheer scale. Training today's cutting-edge deep learning models can take days, sometimes even weeks, and they consume an incredible amount of computational power and energy in the process. It's truly resource-intensive, pushing the very limits of our current hardware. So the burning question becomes, what if there's a fundamentally different way to compute? A paradigm shift, perhaps, that could propel AI far beyond its existing constraints and unlock capabilities we can, well, barely imagine today.
That's precisely the central question guiding our exploration, and it's a pivotal moment, really, in technological history. While AI has made incredible strides, evolving rapidly on the back of classical computing, this ceiling you're sensing isn't necessarily a hard stop, but it absolutely signals a profound need for a new way of thinking, a new computational paradigm. And this is exactly where quantum computing steps into the spotlight. It's truly a next-generation technology poised to break through that classical ceiling, supercharge machine learning, and in doing so, redefine the entire future of AI. We're talking about the exciting emergent field of quantum AI, where the often peculiar, counterintuitive principles of quantum mechanics merge with the power of artificial intelligence. If we zoom out and connect this to the bigger picture, it means that immense data sets and problems previously deemed utterly impossible could become solvable in mere seconds, moving from abstract theory to tangible reality. So our mission today, for you, our curious listener, is to dive deep into this fascinating convergence. We're going to explore how these two immensely powerful technologies, AI and quantum computing, are not just coexisting, but actively shaping each other. We'll look at what groundbreaking breakthroughs they promise, who the key players are driving this innovation, and what significant challenges still lie ahead. Our goal is to provide you with those genuine aha moments, making what might seem like overwhelming futuristic information crystal clear, incredibly exciting, and profoundly relevant.
All right. Absolutely. And it's a story rooted in decades of innovation. So let's start by looking more closely at this ceiling AI is currently bumping up against. From its initial concepts back in the 1950s, AI has been on an incredible accelerating journey. We saw the rise of more sophisticated machine learning techniques in the 90s, the explosion of deep learning in the 2010s, and now we're immersed in the era of highly sophisticated generative AI models, like the large language models many of us interact with every day. This impressive evolution has largely been fueled by continuous hardware improvements, particularly the advent of powerful GPUs or graphics processing units. These GPUs excel at parallel processing, right, enabling AI to handle the extensive simultaneous computations needed for training vast neural networks and deep learning models. But even with these remarkable advancements, we're now seeing inherent limitations. In terms of model efficiency and just the sheer amount of hardware required to keep pushing generative AI forward, there's a tangible sense that we're demanding more than classical physics can comfortably deliver.
You've hit on a critical point. The journey of classical computing to bring AI to its current state has indeed been one of remarkable symbiotic evolution. But as you suggest, there are undeniable constraints that signal this ceiling. Let's detail what these limitations truly mean for AI. First, we face data and power-intensive training. Modern AI models, especially those deep learning networks that achieve such impressive feats, demand not just enormous data sets, but also an astronomical amount of computational power. Training these large-scale models can, as you mentioned, take weeks and consume vast energy resources. I mean, we're talking about the energy consumption equivalent to small towns for some of the biggest models. It's staggering. To give you some context, state-of-the-art language models are trained on hundreds of billions or even trillions of words. Now compare that to a well-educated human who encounters, approximately 200 million words in their entire lifetime. This raises an important question. Does simply throwing greater data volumes at a problem inherently translate to better outcomes, or are we approaching a point of diminishing returns? Humans learn remarkably efficiently with significantly less data, inferring complex rules from, sparse examples. Furthermore, we're actually nearing the limits of readily available high-quality data. AI models have already been trained on vast amounts of existing human knowledge, leading to concerns about data scarcity. And this over-reliance on synthetic data, data generated by other AI models, risks degrading overall model performance. It highlights a growing importance of perhaps smaller, more carefully curated, high-quality data sets. Second, beyond the sheer data and power demands, another critical area where classical AI hits its ceiling is optimization bottlenecks. Imagine trying to find the single best path through a maze with a million possible turns. Classical computers typically have to explore these options largely one by one, or through clever but still sequential heuristics. This sequential approach becomes a significant barrier when AI relies heavily on solving incredibly complex optimization problems. Things like efficiently training neural networks or fine-tuning their myriad of hyperparameters. It's a huge computational task. Classical systems are limited to exploring possibilities one at a time, which makes tasks like optimization, complex simulations, or modeling highly intricate systems incredibly challenging and time-consuming. Third, and closely related, even with the most powerful supercomputers we have today, we're hitting computational limits, particularly with problems involving combinatorial optimization. This involves testing an enormous number of possibilities, where the number of potential solutions grows exponentially with the problem size. Think factorial growth. Even the fastest classical systems struggle with such vast search spaces, often resorting to approximations rather than finding truly optimal solutions. Fourth, and perhaps more fundamentally from a practical standpoint, many complex AI models still largely function as black boxes. We can observe their inputs and their impressive outputs, sure, but their internal decision-making processes often lack interpretability and transparency. This isn't just an academic concern, it can be a significant hurdle in critical applications like healthcare, autonomous driving, or finance. Areas where understanding why an AI made a particular decision is paramount for trust, accountability, and frankly, safety. This lack of clear insight limits our ability to truly understand and refine these powerful systems.
This is a pivotal moment in computing, truly. These limitations clearly signal that to move beyond this ceiling, we need a completely new computational paradigm. We're not just talking about making classical computers incrementally faster or more efficient. We're talking about a fundamental shift in how computation itself happens.
Exactly. Think of it this way. Classical computers, from the smartphone in your pocket to the most powerful supercomputers, all operate on principles that date back to the concept of Turing machines almost a century ago. They use bits, which are definite units of information, existing in one of two distinct states, a 0 or a 1. You can easily visualize this like a simple light switch. It's either on or off with no ambiguous in between.
Right, it's that clear deterministic logic. Provide the same input, and you'll get the same output reliably every single time. That predictability has been the bedrock for all digital computing and, by extension, the entire journey of AI development, allowing systems to learn through reliable, repeated computations.
Quantum computers, however, represent a complete paradigm shift, fundamentally different from their classical counterparts. They operate on quantum bits, or qubits, which behave according to the, mind-bending laws of quantum mechanics. Unlike a classical bit's simple light switch, a qubit is far more complex, more like a dimmer switch that can be set at any point between fully off and fully on. This is due to a principle called superposition, which means a qubit can exist in multiple states simultaneously. It can be 0, 1, and any combination of both all at once. What's even more mind-boggling and truly unique to the quantum realm is entanglement. This is where qubits can become inextricably linked, correlating with each other in ways that classical bits simply cannot. Imagine two entangled coins flipped in separate rooms. If you observe one and find its heads, you instantly know the state of the other no matter how far apart they are. There's an immediate non-local connection. This isn't merely an upgrade to existing computing. It truly redefines the speed and scope of what computation can achieve by moving beyond the limitations of classical physics.
That's a huge conceptual leap. So instead of a classical computer having to search for a hidden key in a vast, sprawling building one room at a time, a quantum computer, because of superposition and entanglement, can, in theory, explore all those rooms simultaneously. If you have the right algorithm, of course. It's like having a million searchers working at once.
Precisely. This allows qubits to process a huge number of potential solutions all at once, offering truly exponential computing power for certain types of problems. However, there's a crucial caveat that's vital to understand. When quantum computers perform calculations, they don't always follow a step-by-step deterministic path to a single fixed answer like 2 plus 2 equals 4. Instead, they explore multiple possibilities and provide probabilistic outputs. This means if you run the same quantum computation multiple times, you might get slightly different results each time, with the correct or most likely answer emerging with the highest probability. The art of quantum algorithm design is to structure the problem so that the answer we're looking for is the most probable outcome. While this probabilistic nature means quantum computers are generally unsuitable for tasks requiring absolute consistent certainty every single time, like, say, basic arithmetic, it opens up entirely new avenues for solving problems that classical computers find intractable. It's a trade-off, but one that could unlock immense, otherwise unreachable potential for complex challenges.
So if quantum computing operates on such fundamentally different principles, how do these two immensely powerful technologies, classical AI and quantum computing, actually start to work together? Because the idea isn't for one to completely replace the other, is it? It's more synergistic.
Not at all. That's a crucial distinction. The real beauty here is that quantum computing and AI can complement each other in many significant and multi-directional ways. It's not a zero-sum game. It's about deep synergy, creating a hybrid approach that could substantially reduce algorithmic complexity, improving the efficiency of computational processes and resource allocation far beyond what either technology could achieve on its own. It's truly a two-way street where each technology helps to advance and refine the other.
That perfectly frames our next point. How quantum computing can supercharge AI. What are the direct, tangible benefits that quantum brings to the table for artificial intelligence, making it smarter and faster?
Well, one of the most direct and exciting benefits comes through quantum machine learning, QML. This involves leveraging quantum algorithms and principles to train AI models, which could dramatically speed up how fast AI learns, processes information, and adapts. Think of it this way. Many deep learning tasks involve incredibly complex matrix operations, right? And quantum computers possess the inherent capability to perform these operations far faster and more efficiently than even the most powerful classical systems. This directly translates to accelerating deep learning training, potentially massively accelerating it.
And what about specific real-world applications? Where do we anticipate quantum offering this exponential performance boost for AI?
One of the most promising and immediate areas is enhanced optimization. As we discussed, classical AI often struggles with complex optimization problems because it has to explore possibilities sequentially. Quantum algorithms, such as the Quantum Approximate Optimization Algorithm, QAOA, and the Variational Quantum Eigensolver, VQE, are powerful tools that leverage quantum principles to explore vast numbers of possibilities simultaneously. Think of them as super efficient search engines for finding the absolute best solution in incredibly complex optimization landscapes, far beyond what classical methods can achieve. For instance, in areas like supply chain routing, where finding the most efficient delivery paths can save billions, or in financial modeling to optimize investment portfolios, or even in the complex world of protein folding for drug discovery. Quantum algorithms can evaluate exponentially more possibilities at the same time than classical algorithms. This speed and depth of analysis would be game-changing for any industry that relies on precise, fast decision-making. We're already seeing this in action. Siemens, for example, leveraged a quantum AI hybrid approach to optimize their polymer reactor design. The BMW Group also uses a hybrid quantum traditional computing model in materials science and automotive engineering, where quantum components take on those complex combinatorial optimization subproblems. Beyond optimization, quantum systems are inherently excellent at solving high-dimensional problems, making them ideal for better data processing and pattern recognition. This is crucial for tasks like image processing, where an AI needs to understand complex visual information, or a natural language understanding, to discern subtle patterns in human speech and text. And particularly in cutting-edge fields like genomic sequencing, which involves massive high-dimensional data sets. Classical computing systems currently face a well-known capacity shortage problem for such high-dimensional data, and quantum computing could essentially eliminate that bottleneck by processing these complex data landscapes with unprecedented efficiency. Furthermore, this means quantum computers could enable AI to tackle problems that are simply beyond classical reach, leading to entirely new breakthroughs in fields like drug discovery and advanced materials science, allowing us to design molecules and materials with tailored properties we couldn't even model before. For example, Roche, the Swiss pharmaceutical giant, and Cambridge Quantum Computing, or CQC, are already collaborating. They're using AI, ML, and quantum computing specifically for Alzheimer's disease research and early-stage drug development. Similarly, in the world of finance, JPMorgan Chase and QCware found that using quantum deep learning to enhance classical deep hedging frameworks led to more efficient training of complex financial models. It offered a tangible advantage. Lastly, we could see significantly improved natural language processing, NLP. The quantum advantage in handling complex data structures could mean quantum-enhanced NLP models could process the intricate nuances of language more efficiently and accurately. This could lead to a new generation of far better chatbots, more accurate and nuanced translators, and genuinely more capable AI assistants than we have today. Understanding context and intent with a depth currently, well, unimaginable.
That sounds incredibly powerful, with quantum directly enhancing AI capabilities across the board. But as you mentioned earlier, this is a two-way street. How is AI in turn playing a critical role in advancing quantum computing itself, making these groundbreaking systems smarter, more reliable, and ultimately more practical?
That's a fantastic question because AI's role in accelerating quantum development is absolutely indispensable. AI has this incredible power to make complex systems work better and faster, and this extends directly to the nascent field of quantum computing. AI can optimize performance using machine learning and drive innovation through generative AI across various aspects of quantum systems, from hardware to algorithms. Companies like IQM, for instance, are heavily investing in these areas, recognizing that AI is key to refining their quantum offerings.
So let's break that down. How exactly does AI accelerate quantum computing development in practical terms? What are the key areas?
Okay, a critical area is AI in auto-calibration. Quantum computers are, by their very nature, incredibly delicate and sensitive machines. Maintaining their stability and ensuring they perform optimally often requires precise, continuous calibration, which can be a manual and time-consuming process. Tedious, really. By applying machine learning in these calibration routines, quantum computers can effectively learn to tune themselves, becoming much easier to use and maintain. This translates to a smoother user experience for researchers and developers, lower operational costs for running these complex machines, and less spiralized training required for operators. Essentially, AI makes running a quantum computer more efficient and accessible. Perhaps even more vital for the future of quantum computing is the role of machine learning for error correction and mitigation. QECQEM. Quantum systems are famously susceptible to noise and errors from their environment, decoherence, gate errors, you name it. This is a major hurdle for achieving reliable performance and running longer, more complex computations. AI can significantly improve how quantum computers detect, identify, and fix these errors. In fault-tolerant quantum computing, for example, where redundant qubits are used to protect quantum information, the process relies on sophisticated decoder software that analyzes error patterns and identifies where mistakes have occurred so they can be corrected. The most precise and efficient decoders being developed today are powered by AI. Google, for instance, with its DeepMind AI division, developed AlphaQubit, an advanced ML decoder that achieved significant error reduction. It showed a 6% improvement compared to older tensor network methods and a substantial 30% improvement compared to correlated matching techniques. That's a big deal. IBM, for its part, has an ambitious roadmap to create a large-scale, fault-tolerant quantum computer by 2029, with AI-powered error correction being a core component. Companies like IQM are also deeply involved, developing AI-powered decoders for their fault-tolerant quantum computers. And they're using deep learning models, like transformer models, to predict and correct errors before the user even runs their computations. Imagine that predictive error correction. Their noise-robust estimation, NRE method, has already been shown to outperform traditional error mitigation techniques. AI is also crucial for optimizing quantum algorithms. Running useful quantum applications requires efficiently translating abstract quantum operations into instructions that a specific piece of quantum hardware can execute. This process needs transpiler software that optimizes these translations. It's like compiling code, but much trickier. AI helps design smarter transpilers that can efficiently map industrial-scale quantum algorithms onto the unique architectures of various quantum computers, making quantum computing faster and more practical. Finally, AI even plays a pivotal role in quantum chip design itself. Fault-tolerant quantum computers rely on special error-correcting codes, and the choice of these codes directly influences the optimal design of the quantum processor. AI can help discover better, more efficient error-correcting codes that minimize the number of qubits needed for error correction and reduce computation time. This creates a direct feedback loop between fundamental code development and the physical design of quantum processing units, QPUs.
This sounds like a virtuous cycle, really, with each technology propelling the other forward. It's quite elegant. So what does this all mean for the current landscape? With such profound synergy, what does the quantum AI frontier look like today? And who are the major players driving this innovation? Because it really sounds like a lot of theoretical work is quickly becoming very practical and tangible.
You're absolutely right. The field is rapidly transitioning from abstract theory to very tangible applications and hardware. Today, companies, governments, and startups globally are largely focused on developing foundational quantum research while also identifying and implementing immediate, impactful use cases for this converged technology. This intense activity demonstrates that quantum AI is far more than just a theoretical concept. Early-stage applications are already being explored, and major tech giants are pouring significant resources into making this future a reality.
Let's talk about some of those major tech giants and their initiatives. Who are the leading forces in this rapidly evolving space? Maybe start with Microsoft.
Okay, Microsoft Azure Quantum is a truly significant player, providing a comprehensive ecosystem. Launched back in 2021, it's a public cloud-based quantum computing platform. It offers a range of hardware, software, and solutions. They support various quantum hardware architectures from partners like Quantinuum, IonQ, and Atom Computing, giving users flexibility. On the software side, they developed Q-Sharp, a dedicated quantum programming language, along with an SDK and the Azure Quantum Resource Estimator. That estimator helps estimate the computational resources needed for fault-tolerant algorithms, which is crucial for planning large-scale quantum computations. What makes Microsoft's hardware ambition particularly noteworthy is its pursuit of a topological quantum computer. This is a really different approach. This design aims to create qubits that are inherently resistant to error by utilizing exotic entities called Majorana quasiparticles. It's based on some pretty advanced physics. In September 2023, their researchers found compelling evidence consistent with the creation and control of these quasiparticles, a crucial step. Then, in February 2025, they reported a major milestone with the creation of Majorana 1, hailed as the world's first quantum chip powered by a topological core architecture. They used something called topoconductors and a new single-shot method for fermion parity measurement. What makes this a truly significant breakthrough is that it isn't just about packing more qubits. It's about making them inherently more stable and resistant to environmental noise and errors. It tackles one of the biggest hurdles in quantum computing from the ground up. This fundamental resilience could dramatically simplify the path to building truly large-scale, fault-tolerant quantum computers. Beyond core hardware, Microsoft is making significant strides in qubit virtualization. Think of it like software making hardware better. In November 2024, working with Atom Computing, they achieved a new record of 24 entangled logical qubits on a neutral atom processor. They demonstrated sophisticated error detection and correction, including the first on-record demonstration of loss correction in a commercial neutral atom system. That's really important for practical computation. Earlier in 2024, they created 12 logical qubits with Quantinuum's trapped ion computer, achieving error rates 800 times better than without this virtualization. It shows how software layers can dramatically improve the reliability of existing quantum hardware. For quantum communication, Microsoft and Photonic also performed a teleported CNOT gate between qubits physically separated by 40 meters. This confirmed the potential for remote entanglement necessary for long-distance quantum communication networks. Very cool stuff. And let's not overlook Azure Quantum Elements, launched in 2023. This initiative intelligently combines AI, high-performance computing, HPC, and quantum tools specifically for accelerating breakthroughs in materials science, chemistry, and pharmaceutical research. It leverages physics-based AI models. For instance, in January 2024, Microsoft and Pacific Northwest National Laboratory used AI and HPC to model and screen 32 million new candidate materials for a more efficient rechargeable battery. And they actually found a single, highly promising candidate out of all those millions. That's the power of this combined approach. In July 2024, they released a generative chemistry tool and an accelerated density functional theory tool, further enabling rapid molecular design. Most remarkably, they solved a practical chemistry problem, catalytic reactions producing chiral molecules, using two logical qubits integrated with AI and cloud HPC. This was the first time an HPC system, AI, and quantum computing hardware have been deployed together to solve a specific scientific problem. It really highlights the power of their hybrid approach. They've also partnered with 1910 Genetics for drug discovery using these tools.
That's an incredibly comprehensive overview of Microsoft's efforts, covering hardware, software, virtualization, communication, and applications. Very impressive. What about Google? Another giant in both AI and quantum. What are the recent highlights?
All right, Google Quantum AI has also been making significant headlines, particularly with their hardware development. In December 2024, they announced their Willow processor, a 105 qubit superconducting quantum computing processor. Google claimed two significant accomplishments with Willow. First, that it can reduce errors exponentially as qubits scale, achieving what they call below threshold quantum error correction. That's the holy grail in theory. And second, that it completed a random circuit sampling RCS benchmark task in just 5 minutes. They calculated this task would take today's fastest supercomputers an astonishing 10 septillion years. That's 10 with 25 zeros, a massive claim of quantum supremacy. They also notably improved coherence time from their previous Sycamore processor's 20 microseconds to a more robust 100 microseconds. That's important for longer computations. However, it's important to frame Willow's achievements within the current context. While impressive, there are caveats. The logical error rates reported, around 0.14% per cycle, remain orders of magnitude above the 10th levels generally believed necessary for running meaningful, large-scale quantum algorithms like Shor's algorithm for breaking encryption. To put that in perspective, imagine trying to hit a tiny target with a shotgun when you actually need the precision of a laser. You need much lower error rates for complex tasks. The demonstrations have largely been limited to quantum memory experiments, not yet showing below-threshold performance of logical gate operations required for universal fault-tolerant computation. So some observers caution that it remains a research prototype squarely in the noisy intermediate-scale quantum NISQ era, meaning practical error-corrected applications are still some way off. Google itself acknowledges this, stating they are still at least 10 years out from breaking RSA, which is a key benchmark for fault-tolerant quantum computing. Nevertheless, their development of AlphaQubit, the ML decoder with DeepMind, is a crucial step in showing how AI can mitigate these quantum errors, even in the NISQ era.
And IBM, of course, has been a long-standing leader, pioneering early quantum systems. What are they focusing on these days?
Indeed, IBM continues to push the boundaries with both hardware and software. They've been in the game a long time. Their Condor quantum processor boasts an impressive 11,121 qubits, making it the largest quantum computer built to date in terms of raw qubit count. And it's integrated into IBM's Quantum System 2, which is a foundational piece of their quantum infrastructure designed to house future larger processors too. They also have an ambitious, publicly stated plan to create a large-scale, fault-tolerant quantum computer by 2029, which is a significant target they're working towards systematically. On the software front, they offer the widely used Qiskit Quantum Programming SDK, which provides a comprehensive suite of tools for building and running quantum programs. It's very popular in the research community. Companies like Merck have utilized Qiskit to simulate complex molecular structures, a task that classical computers struggle with for larger, more intricate molecules. This ultimately helps them better understand potential drug interactions, speeding up parts of the R&D process. Then we have NVIDIA, a company often synonymous with the GPU advancements that have powered classical AI. They're now seriously entering the quantum space. Their CEO, Jensen Huang, stated at VivaTech 2025 that they are within reach of being able to apply quantum computing in areas that can solve some interesting problems in the coming years. NVIDIA is committed to accelerating quantum technology through collaboration and has developed Q2Q. Q2Q is a quantum development platform specifically designed for hybrid systems, acknowledging that the immediate future involves classical and quantum working closely together. They want to enable that bridge. Beyond these tech giants, many other significant players are contributing to the quantum space. It's a diverse field. Companies like Amazon with AWS Bracket, Intel with their quantum research, Rigetti Computing, D-Wave, pioneers in quantum annealing, IonQ, using trapped ion systems, Quantinuum, another leader in trapped ion quantum computing, Pascual, focusing on neutral atom systems, and IQM, developing superconducting processors in Europe. They're all major players. Each has its own priorities and unique technological approaches, often focusing heavily on different aspects of quantum hardware and crucial challenges like quantum error correction. It's a vibrant and highly competitive ecosystem.
That makes sense. Beyond these individual corporate efforts, it's clear the broader ecosystem is recognizing that strategic development and collaboration are absolutely necessary for quantum AI to truly flourish and move beyond the lab. Is that reflected in any specific initiatives?
That's a critical overarching point, and yes, it absolutely is. The Quantum Economic Development Consortium, QEDC, which is a public-private partnership in the U.S., published a comprehensive report in March 2025. It outlined specific synergies and, crucially, offered recommendations for accelerating the QC plus AI convergence. They put forth 3 key recommendations for collective action. First, federal support. The report strongly urges federal agencies to explicitly include support for QC plus AI hybrid technologies in major national initiatives like the National Quantum Initiative Act and the CHIPS and Science Act. This includes funding R&D for what they call heterogeneous computing environments, systems that intelligently integrate QPUs, CPUs, GPUs, and even novel neuromorphic computing architectures. It's about building the full stack. They advocate for fostering crucial infrastructure like heterogeneous computing testbeds at national labs and expanding existing national quantum centers to explore QC plus AI applications. Even non-quantum testbeds, like those focused on grid resilience or advanced manufacturing, could be encouraged to explore QC integration, broadening the application space. The NSF's National AI Research Institutes, for example, could focus on using AI to develop entirely new QC algorithms. Second, the QEDC emphasizes academic research and education. This is really vital for the talent pipeline. They recommend increasing interdisciplinary courses at universities, spanning physics, mathematics, engineering, and computer science to truly leverage student interest in both fields. Partnering universities with QC companies for internships, mirroring successful programs in places like Canada, would better prepare students for industry careers and simultaneously build AI capacity within quantum companies. They also suggest creating multidisciplinary research programs, perhaps akin to the successful Materials Genome Project model. These would fund diverse teams of QC and AI researchers to collaborate on complex challenges like classical algorithms for quantum use cases or large-scale error correction methods. Third, and perhaps most broadly, they call for stronger industry connections. Engaging the quantum computing, AI, and diverse end-user communities is vital to raise awareness, create opportunities for collaboration, and identify critical gaps that government funding or industry partnerships could help fill. Consortia like QEDC and the AI Alliance should actively join forces to bridge these communities. They also suggest promoting QC plus AI development within existing government programs aimed at specific industries, such as Manufacturing USA or the CHIPS R&D program. Events like hackathons and business challenges could also be powerful catalysts to spur interest, foster innovation, and accelerate knowledge sharing across these complex fields. These strategic collaborations are vital. As Dr. Ines de Vega, head of quantum innovation at IQM, predicts, we can expect the first significant breakthroughs in quantum AI to emerge by the end of this decade and the beginning of the next, especially as we transition from the current noisy quantum systems to more stable, error-corrected quantum computers.
This is where the paradigm truly shifts, isn't it? Here's where it gets really interesting. With all this robust development and strategic planning, what tangible real-world impacts can we expect from quantum AI in the coming years? And across which industries might we see these transformative changes by, say, 2035? Because the financial predictions alone are quite significant, aren't they? McKinsey report, for example, predicts quantum computing revenue will grow from about $1 billion in 2024 to as much as $72 billion in 2035. That's massive growth. And Hyperion Research predicts 18% of quantum algorithm revenue will come specifically from AI by 2026 already.
Those numbers truly highlight the immense transformative potential, underscoring that this isn't just academic curiosity, this is big business potential. Let's break down some specific impacts across various industries, drawing from these projections and current research trends. In healthcare, quantum-enhanced AI could revolutionize personalized medicine by modeling the human body at an unprecedented molecular level. This would enable faster and far more accurate drug discovery, much earlier disease diagnosis, and the development of patient-specific treatment plans tailored to an individual's unique biology. We're already seeing this in action. Roche, the Swiss pharmaceutical company, and Cambridge Quantum Computing, or CQC, now part of Quantinuum, are currently using AI, machine learning, and quantum computing for Alzheimer's disease research and early-stage drug development, aiming to unlock new therapies. For chemicals and materials science, quantum AI will accelerate the discovery of entirely new molecules and materials. It will allow simulating complex chemical reactions and material properties with unprecedented accuracy. This means engineers and chemists could design novel catalysts, lightweight alloys, or advanced polymers virtually, vastly speeding up innovation across a multitude of industries. Siemens, for instance, has already leveraged a quantum AI hybrid approach for optimizing their polymer reactor, while the BMW Group uses a hybrid quantum traditional computing model for materials, science research, and automotive engineering challenges, like designing better batteries or stronger, lighter materials. In mobility, we could see sophisticated optimization of traffic flow in real time, highly efficient logistics networks, and smarter electric vehicle EV energy management, all through real-time, large-scale simulations that classical computers struggle with today. It will also likely accelerate the development of truly autonomous vehicle systems and the creation of new lightweight materials for more efficient transportation.
And for something like global logistics and supply chains, which are inherently complex optimization challenges, that seems like a prime target.
Absolutely. In logistics and supply chains, quantum AI will be able to solve optimization problems that current classical computers simply aren't capable of tackling at the required scale and speed. Think about real-time global routing for vast shipping networks, or optimizing inventory across thousands of warehouses simultaneously. This could dramatically increase efficiency, reduce costs, and build greater resilience across vast, complex networks. It's a huge potential impact area. Finance is another sector poised for radical transformation. Quantum systems could offer an unparalleled edge in processing vast, real-time market data. This capability could enhance everything from ultra-precise portfolio optimization and risk assessment to much more robust fraud detection and algorithmic trading strategies. JP Morgan Chase and QC Ware, for example, found that applying quantum deep learning to classical deep hedging frameworks enabled more efficient training of complex financial models, offering a tangible advantage. Finally, within software engineering itself, this convergence will accelerate machine learning model training, solve complex optimization problems integral to software development, and enable entirely new AI architectures that classical computing struggles to support or even conceptualize. Conversely, as we discussed, AI and machine learning will be crucial in improving quantum error correction, optimizing quantum algorithms, and making quantum systems more accessible and easier to program. It's important to reinforce that these breakthroughs are generally beyond what classical systems alone can achieve, positioning quantum computing as a powerful strategic accelerator across virtually every sector that relies on computation and data.
These applications paint a truly incredible, almost futuristic picture. But let's bring it back to Earth slightly. What are the remaining hurdles we need to overcome? And what does the timeline truly look like for this exciting future to become a widespread reality? Because despite all this progress, the timeline for mass adoption of quantum AI remains uncertain, doesn't it? It's not happening tomorrow.
It absolutely does remain uncertain, which is why understanding the challenges is so crucial for anyone looking to engage with this technology. For practitioners and industries, staying agile and well-informed will be key to being best positioned to incorporate new advancements as they emerge. The hurdles are indeed significant. First, hardware limitations are still prominent. We're currently still in what's known as the noisy intermediate scale quantum, or NISQ era. This is characterized by quantum systems having a limited number of qubits, relatively short qubit coherence times, meaning how long a qubit can maintain its quantum state before it loses its information, and high error rates. These systems are highly sensitive to environmental noise, making reliable, large-scale quantum computations incredibly challenging. To reiterate on the Google Willow criticisms we touched on earlier, while impressive, its reported logical error rates still need to improve by orders of magnitude from roughly 0.14% per cycle down to the 10^6 levels, so a million times better for truly industrial relevance. And vastly larger qubit arrays, probably millions of physical qubits to get thousands of logical ones, will be required for practical applications like breaking current encryption. Second, scalability and accessibility are major concerns. The immense cost of building and maintaining these cutting-edge quantum systems, coupled with the inherent challenge of qubit stability and the need for incredibly effective error correction, well, it could slow down widespread deployment and adoption. These aren't machines you'll be buying for your home office anytime soon, or probably ever in their current form. Access will likely remain cloud-based for a long time. Third, and critically, there are significant data loading challenges for quantum machine learning, QML. This is a bit of a paradox. While quantum computers promise exponential processing power, their currently limited qubit memory and slowed data transfer rates mean they can actually take weeks to load and process what classical systems handle in moments when dealing with truly massive classical datasets. This constraint forces a fundamental rethinking of big data for quantum applications. It suggests that QML might need to forge its own distinct path, one that intelligently leverages quantum's unique strengths in pattern recognition and optimization, perhaps, with smaller, higher quality datasets, rather than simply trying to mirror classical AI's brute force approach of feeding ever larger data volumes. It aligns more with a small data philosophy, maybe, where smarter algorithms derive insights from less information.
So given these hurdles, the solution isn't necessarily quantum replacing classical computing entirely, but rather them working together. A hybrid model, at least for the foreseeable future, correct? That seems to be the consensus.
Exactly, that's a vital distinction. The near-term future is undeniably all about hybrid systems. Quantum processors will handle niche, high-value tasks, The specific problems they excel at, like complex optimization or molecular simulation, while classical systems continue to manage the broader, more general operations, including pre- and post-processing quantum data, managing workflows, and handling tasks where quantum offers no advantage. This strategically leverages the complementary strengths of both architectures. NVIDIA, for instance, has developed its SUDE-AQ platform specifically for these hybrid systems, aiming to make that integration seamless for developers. The BMW Group provides a great practical example. They use a hybrid model where classical computing handles large-scale simulations for vehicle design, and quantum computing is specifically brought in for sub-problems like solving complex optimization tasks within materials science or simulating quantum-level interactions in new battery components. This approach allows us to get the best of both worlds as quantum technology continues to mature. Looking further out, the potential is even more profound. Quantum computing can significantly accelerate AI algorithms and improve current technology toward the long-term vision of artificial general intelligence, AGI. The combination of quantum machine learning, QML, and advanced generative pre-trained transformers, GPTs, could lead to AI systems that are not only faster and more efficient, but also potentially more capable of understanding and interacting with the world in a genuinely human-like manner, maybe even exhibiting creativity or common sense reasoning. Quantum large language models, QLLM, could specifically address the scalability issues that currently limit the development of larger and more complex AI models, which seems essential for achieving AGI. This brings to mind Richard Feynman's famous insight: nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. This powerfully suggests that natural intelligence itself might, at its deepest level, be driven by quantum effects. If true, quantum computers might be necessary to truly replicate it. Furthermore, there's the intriguing possibility of deploying quantum computing at the edge for secure and private local AGI systems. This involves embedding quantum capabilities, maybe specialized quantum chips or algorithms run via the cloud, into local devices, harnessing quantum's inherent randomness and immense processing power to process local inputs in real time. This decentralizes AI processing, significantly enhancing data privacy and security. Your data doesn't have to go to a central server, and it could mitigate some of the risks associated with centralized AI control, often depicted in science fiction scenarios like Skynet. It's about bringing powerful, intelligent capabilities closer to the user with inherent privacy safeguards built in.
That's a truly fascinating long-term vision, spanning from practical hybrid systems today to decentralized AGI tomorrow. Wow. But for the more immediate future, what are the concrete timelines and predictions we're seeing from experts for when this convergence of quantum AI will really take hold in a practical sense? When might we see that quantum advantage?
There's a cautious but growing optimism and some converging timelines from key figures in the field, though always take predictions with a grain of salt in such a rapidly moving area. Google Quantum AI's director of hardware, Julian Kelly, stated in March 2025 that we're about 5 years out from a real breakout, kind of practical application that you can only solve on a quantum computer. A true quantum advantage for a specific, valuable problem. So around 2030, perhaps? Jensen Huang of NVIDIA echoes this sentiment, saying they are within reach of applying quantum computing to solve interesting problems in the coming years. IQM, a European quantum hardware leader, has a roadmap aiming to achieve quantum advantage as early as 2030. And their head of quantum innovation, Dr. Hans de Bega, predicts the first significant breakthroughs in quantum AI to emerge by the end of this decade and the beginning of the next, particularly as we transition to more stable, error-corrected quantum computers. IBM, as we mentioned, has that clear goal for a large-scale, fault-tolerant quantum computer by 2029. So the late 2020s to early 2030s seem to be a key window many are targeting for major milestones. As these timelines suggest, the market is poised for substantial growth. McKinsey, as you noted, predicts quantum computing revenue will surge from $1 billion in 2024 to as much as $72 billion by 2035. Achieving this will depend on several key advancements happening concurrently. We need better quantum hardware with more stable qubits, improved coherence times, and significantly larger qubit counts. That's fundamental. We also need scalable quantum machine learning algorithms that can effectively harness this hardware. Algorithm development is just as crucial. And of course, successful commercialization of these technologies into viable products and services that companies actually want to buy and use. Ultimately, success will also depend heavily on collaborative innovation, a continuous exchange between researchers, tech giants, governments, and end users. Crucially, as we advance, dedicated attention to ethics, data use, and cybersecurity will be paramount. We need to ensure the safe, fair, and responsible usage of quantum AI, especially concerning sensitive issues like privacy, security protocols like breaking current encryption, and the potential impact on the job market. And speculating further, this convergence could eventually make quantum computing far more accessible and practical, perhaps with costs decreasing over time. Maybe eventually reaching levels comparable to the high-memory GPUs used in AI today, democratizing access to this incredible power likely through cloud platforms.
So to bring it all back, the fusion of quantum computing and artificial intelligence is really not just theoretical hype. It's a transformative technological advancement. It's poised to redefine computing and, by extension, human capabilities themselves. It's about solving problems that classical computers simply cannot, pushing AI to be more efficient, faster, and more powerful than we ever thought possible, truly unlocking a new era of innovation.
Indeed. And if our deepest scientific understanding of nature, from the smallest particles to the very fabric of reality, is fundamentally quantum, which it seems to be, then what does this convergence of quantum AI truly reveal about the fundamental nature of intelligence itself, both artificial and perhaps even natural? How will it reshape our understanding of consciousness, creativity, and the very future of human-machine interaction? That's a thought worth exploring long after this deep dive.
Absolutely. A profound question to end on. Thanks for diving deep with us today. We hope this exploration has given you a clearer, more exciting picture of this incredibly dynamic frontier and sparked your curiosity to learn even more about the future of quantum AI.